Alright, in this video we're talking about waves and basically the introduction to waves. Now, a wave is a disturbance which travels through a medium, transferring energy from one point to another without any actual displacement of the medium. Now, a very typical example, a very good example of waves is water wave. If you should drop a stone into a bucket of water, you notice water ripples, all right, or the movement, tiny little movement in the water. Let's say this is our stone. You notice some movement in the water. Now those movements are disturbance which spread out in the medium, which is water. They travel in the medium, but then you notice that there's actually no displacement. There's no actual displacement of the water itself. All right. So a wave is a disturbance. That's a typical example of a wave. A wave is a disturbance that travels, spreads out in the medium, as seen in those water ripples. All right. But then there is actually no displacement of the medium. Now, not all waves actually require a medium for their propagation. You need to have this at the back of your mind. It's very important. Remember, our definition said a wave is a disturbance that travels through a medium. But please take note, not all waves require a material medium for their propagation. Now, the waves that require a material medium for their propagation are known as mechanical waves. A very good example of mechanical waves is sound wave. Sound is a mechanical wave. It requires a material medium. The material medium for the propagation of sound is air, usually air. All right, and then we have water waves. The material medium for propagation of water waves is water. The wave travels in water. You also have waves in a rope or string. The medium for propagation is the string or the rope. For instance, the guitar string. Okay, the material of propagation is the string. So all these guys are mechanical waves. Mechanical waves, a material medium is needed, as seen in these examples. Now, the waves that do not require a material medium for their propagation are known as electromagnetic waves. The electromagnetic waves, these are the waves that do not need a medium for their propagation. Example, we have the gamma rays, we have the X-rays, we have the ultraviolet rays, we have the visible light, which is simply light rays, we have infrared rays, we have microwaves, we have radio waves. Now there is a simple acronym for this that you can use to memorize the electromagnetic waves. We have what we call the Zol, Vim, Rad. Alright, simply written as Ga, Zol, Vim, Rad. Alright, so this is a simple acronym we can use to memorize the electromagnetic waves. Ga here stands for gamma, X stands for X-rays, all here stands for ultraviolet rays, ultraviolet rays, and V stands for visible light, visible light. I stands for infrared. M represents microwaves, and rad here stands for radio waves. So these are the electromagnetic waves. Do not forget, the electromagnetic waves do not need a medium for their propagation. All right, whereas the mechanical waves need a medium for their propagation. Now, also, waves can be classified into um, transverse and longitudinal. Now, the transverse waves are waves in which the direction of wave motion is perpendicular to the direction of the vibration producing the motion. All right, direction of wave motion is perpendicular to the direction of the vibrations producing the motion. Okay, this can be illustrated using this diagram. Let's say this is what we have for our transverse wave. This is how the wave travels. It travels in this direction. Alright, so the wave travels in this direction. This is the direction of wave motion. Now the particles will vibrate within this medium here. Okay, we can have a particle at this point here. Have a particle at this point, then it moves in this direction. Particles keep on vibrating. We have the particles here, just like that. Now here you notice that the particle here, this is where we have the particle initially, this point here. You notice that the particle and the direction, they are perpendicular. We can draw straight lines here. You see that they are perpendicular. They are at 90 degrees to each other. The same case here. Okay, the direction of wave motion, okay, perpendicular to the vibrations of the particles, perpendicular to the direction of the vibrations producing the motion, or perpendicular to the vibrating particles. Okay, so this is how we illustrate transverse waves. Now you need to have it at the back of your mind that all electromagnetic waves are transverse. Examples of transverse waves, we have all electromagnetic waves. They occur like this. Okay, their wave motion is perpendicular to the vibrating particles. So all electromagnetic waves are transverse, and we've talked about the electromagnetic waves already. The gamma rays, the X rays, and the likes, they are all transverse waves. Light is a transverse wave. All right, other examples of transverse waves, we have water wave. Okay, water wave, water waves. We also have waves on a rope or string. All right, they also move in this up and down manner. All right, so waves where the direction of wave motion is perpendicular to the direction of the vibrations, okay, as seen here, we call them transverse waves. Here these are just the particles. You see that the particles are always perpendicular as we progress. Direction of wave motion perpendicular to the vibrations of the particles producing the motion. So that is transverse waves. Now closely related to transverse waves are the longitudinal waves. Now the longitudinal waves are waves in which the direction of wave motion is parallel to the vibrations producing the motion. Now in longitudinal waves, the vibrations and the vibration of the particles and the direction of wave motion are in the same direction. Now longitudinal waves usually give rise to adjacent compressions and expansions, also known as rarefactions. A very good example can be seen, or a typical example of a longitudinal wave can be seen using this diagram. The diagram I'm trying to draw here. So this is a typical example of a longitudinal wave. At some point you notice that the waves or the spring is actually very close to each other. Here they are expanded, here they are very close to each other, here they are expanded, here they are very close to each other, and here they are expanded. So say longitudinal wave give rise to adjacent compressions. This is a compression. Adjacent compressions and rarefactions or expansion. This is a rarefaction, also known as expansion. So in longitudinal wave, we see adjacent compressions and rarefactions. Immediately the first compression, the next one is a rarefaction, and then immediately the rarefaction is a compression, rarefaction, compression, rarefaction, like that. So this is what a longitudinal wave looks like. Now the particles are inside this material here. You notice that the particles move in this direction. Wave motion is also in this direction. The compressions and rarefactions occur in this direction. They move like this on the horizontal, and then the particles also move in the same direction. So you see that they are parallel to each other. In other words, they are in the same direction. All right. Now, in transverse wave, do not forget transverse waves. We have an up and down like motion. Okay, the particles are perpendicular. Vibrations of the particles are perpendicular to the direction of wave motion. Okay, so we have compressions and rarefactions here. Here we have an up and down motion, and in this up and down motion, the highest point attained is what we call the crest of the wave. The crest of the wave, and here the minimum point attained is what we call the trough. So have this at the back of your mind. We have crest and trough. All right. Transverse waves will give rise to crest and trough, whereas in a longitudinal wave we have adjacent compressions and rarefactions. Now we'll be talking about some terms used in describing waves. We have what we call the amplitude. All right, the amplitude is the maximum displacement of a particle from equilibrium position. To understand this better, I'm going to be working with a diagram for the transverse waves. All right, so this is what our transverse wave looks like. So let's talk about each term one after the other. Now, the amplitude first is the maximum displacement of a particle from equilibrium or rest position. This is taken as our equilibrium or rest position, the long horizontal line. All right. Now, the maximum displacement attained is what we call amplitude. Amplitude is simply the displacement from equilibrium position. So this is your equilibrium position. The maximum displacement the wave attains is what we call amplitude. So we have amplitude. All right, the displacement from equilibrium to this point. That's the difference between this point and this point is what we call amplitude. Maximum displacement attained. Now, amplitude is different from crest. Crest is just a point, a location. All right, crest is a point on the wave, whereas amplitude is the difference between 2 points, a displacement on the wave. This is crest, and then this is amplitude. So the maximum displacement we have on the wave from equilibrium position is what we call amplitude. Now we also have what we call the wavelength. Now the wavelength is the distance between two successive crests or trough of a wave. This is a crest. Do not forget we've talked about crest before. The highest points attained. So this is a crest and this is another crest. The distance between two successive crests. Distance between this crest and this crest is what we call wavelength. And wavelength is represented with the symbol lambda. That's the symbol for wavelength. Wavelength is symbol represented with the symbol lambda, and it is measured in meters. All right. Though we can also have other units like the centimeter, but meter is the standard unit for wavelength. So wavelength is the distance between two successive crests or the distance between two successive troughs. This is a trough. So the distance from here to here. Don't mind my diagram is not very straight, but let's just go with it. So the distance between two successive crests or trough of a wave is what we call wavelength. And don't forget the symbol is lambda. This is how we write lambda. It's a Greek alphabet measured in meters or centimeter. All right. Amplitude, on the other hand, is also measured in meter and centimeter. Now, wavelength can also be defined as the distance traveled by a wave when it makes one complete cycle. One cycle is simply the distance from this point down to this point. All right. Now you notice that okay, let's use this. This is what a cycle looks like. If you should divide this into two, we have half cycle and then another half cycle. So that's exactly what we have here. This is half cycle, this is another half cycle. Half cycle plus half cycle gives us one cycle. So one cycle is simply one top and one base, or one bottom. All right. So the distance the wave will travel when it makes one complete cycle can also be called wavelength. So we can say from this point, from the origin down to this point, we have wavelength also. All right. So wavelength is also the distance traveled by a wave, all right, when it makes one complete cycle. So this is one cycle, this is another one cycle. In this way we have two cycles. We have one and then two. This is half a cycle plus another half, giving us one. This is one and a half, and then this is two. So the wavelength can also be defined as the distance traveled by a wave when it makes one complete cycle. Don't forget, the symbol for wavelength is lambda. Now we also have what we call the period of a wave. Period of a wave. The period is simply the time taken to make one complete cycle or oscillation, and it is represented with the symbol T. Okay, mathematically, period is equal to time divided by number of oscillation. The time taken to make one complete oscillation. All right, time period is time taken to make one complete oscillation. And mathematically, period is time divided by number of oscillation. Now we also have the frequency. Now the frequency, on the other hand, is the number of cycles made in 1 second, and its symbol is F. And mathematically, frequency is equal to number of cycles or oscillation. Number of oscillation. Alright, please, number of oscillation is still the same as cycle. In this case, we'll be using cycles most times. Number of oscillation, also known as cycles, divided by the time taken. Alright, so period is time taken to make one oscillation or cycle, and mathematically is equal to time over number of oscillation or cycle. Here, frequency is number of oscillation or cycle divided by time. Frequency is simply the number of cycles taken in 1 second. Alright, now period is measured in seconds, and then frequency is measured in hertz. Those are the units of measurement for the two of them. Now you notice something here. In period, time is at the numerator, number of oscillation is at the denominator. In frequency, we have number of oscillation at the top, time at the denominator. Alright, that's to say they are inverse of each other. So another very important equation is this equation: period and frequency are inverse of each other. That's to say period is equal to 1 over frequency, or frequency is equal to 1 over period. Alright, this equation is actually very important, so you just have to take it down because we'll be using it as we progress. Period 1 over frequency, frequency 1 over period. They are simply inverse of each other. Now we also have what we call the wave speed. Now the wave speed is simply the distance traveled by a wave in 1 second, and its symbol is V. Okay, now mathematically, okay, wave speed is measured in meter per second. Mathematically, the wave speed is equal to frequency times wavelength. Frequency times wavelength. But do not forget, frequency is also equal to 1 over period. So in place of F, we can put 1 over period, and then we'll have times wavelength, and that will give us wave speed equals wavelength over period. So these are the two equations we have for wave speed. So also take it down, as it is also very important. So far we have some very important equations: wave speed, frequency times wavelength; wave speed, wavelength over period; frequency 1 over period; period also equals 1 over frequency. Now we're going to be solving some problems on waves, applying the equations we've just derived to solve some problems. Now the first problem we have here, exercise 1, this one says a wave has a frequency of 2 hertz and a wavelength of 30 cm. So the velocity of the wave is. Now I usually tell my students, whenever you're confronted with a question that has to do with calculations in physics, the best way to solve it is to bring out all the parameters you're given and then look out for the formula that will perfectly suit that question. So now let's bring out all the things we're given. Here they said a wave has a frequency of 2 hertz. So bring it out. Frequency is equal to 2 hertz and a wavelength of 30 cm. So we have wavelength lambda equals 30 cm. They say the velocity of the wave is, so we are looking for v. Now, what is the formula that connects frequency, wavelength, and v? That's the formula that has all these parameters. Now, the only formula that has them is v equals frequency times wavelength. This is one of the formulas we derived previously. Okay, so we have wave speed equals frequency times wavelength. So we can just use this to calculate. But before we calculate, you realize that there are options here, and all the options here have meter per second, meter per second, meter per second. There is no centimeter per second here. So that's why we need to convert this wavelength here. Wavelength is in cm. We don't just use it like that to solve here, else we are going to get a wrong answer. So we convert this to meter so that it can rhyme with what we have here. Our units must be uniform. If we have cm here, all right, the options should also be in cm. If the options are in cm, we can use this like this. But if the options are in meters, we have to convert the centimeters to meters. So how do we convert from centimeters to meters? We simply divide by 100. So we have 30 divided by 100, and then this will give us our answer in meter. So 30 divided by 100, that will give us 0.3 meters. So we have 0.3 meters as our wavelength. Now we can plug into our formula and solve. We have wave speed equals frequency times wavelength. What's our frequency? 2 hertz. So simply say wave speed will be equal to 2 multiplied by wavelength is 0.3. So we have multiplied by 0.3, and that will give us 2 times 0.3, which is 0.6 meters per second, and that is option D. Now let's also attempt this question. This one here says the wavelength of ultraviolet radiation is 400 nanometers. So again, we bring out all our parameters. We have wavelength equals 400 nanometer. It said if the speed of light in air is 3 times 10 raised per 8 meter per second, write it out again. V equals 3 times 10 to power 8 meters per second. Then the frequency of ultraviolet radiation is, we are looking for F in this case. So again, we try to bring out the formula that connects everything. And what is that formula that connects wavelength, wave speed, and frequency? The formula is wave speed, V, is equal to frequency multiplied by wavelength. So we are looking for F. We simply go on to make it the subject of the formula. And how do we go about that? We divide both sides by lambda. We have V over lambda equals F lambda over lambda. This is going to cancel out lambda, and then we're going to have F equals V over lambda. So frequency is simply wave speed divided by wavelength. So now we go in to plug into our formula or our equation. But before we do that, you see that lambda is not in the actual unit. Remember I said you can have meter or centimeter. Now in this case, you discover that your wave speed is meter per second. Here we have nanometer. And I mentioned earlier that your units must be uniform. So since we have nanometer here, we need to ensure it's in unison with meter. So how do we convert nanometer to meter? Nano here is a prefix, and nano means 10 raised to power minus 9. So we have, this is going to give us 400 times 10 to power of minus 9 meter. So now we can substitute into our formula F equals V over lambda and solve. So we have frequency equals V, which is 3 multiplied by 10 to power 8 divided by 400 nanometer, which is like 400 times 10 to power of minus 9. So at this point, we simply use our calculator to solve. Alright, so on solving, we arrive at frequency equals 7.5 times 10 to power 14 hertz, and that is option D. Now moving on, we have another question here, a very interesting question. This one says the diagram above represents a transverse electromagnetic wave traveling with speed 3 times 10 raised per 8 meters per second. What is the frequency of the wave? Alright, so here we have a diagram and we have 0.3 meters on this diagram. So let's try to bring out what we have, the information that was given to us. First, they say the diagram above represents a transverse electromagnetic wave traveling with a speed. So we have speed given to us, and speed is equal to 3 multiplied by 10 to power 8 meter per second in this case. So what is the frequency of the wave? We are looking for frequency. Frequency is unknown. So how do we get frequency? Now there's only one formula that relates wave speed and frequency, and that is V equals frequency times wavelength. V equals frequency times wavelength. To get frequency, we'll make frequency subject of the formula, and we have frequency equals wave speed divided by wavelength. So how do we calculate frequency? To calculate frequency, we need wave speed, which was given to us. We also need wavelength. Now wavelength was also given to us in the diagram, but it is not very clear. Alright, so how do we get it now? Now you realize that on this diagram we have 0.3 meters. Now remember, I gave a definition prior to this time, and what's that definition? We said wavelength is the distance traveled by a wave when it makes one complete cycle. On this diagram we have how many cycles? We have 3 cycles. This is one cycle, this is one cycle, this is 2, and then this is 3. So we have 3 cycles to be 0.3 meter. Now our wavelength is simply one cycle, the distance for one cycle. So how do we go about this? It's very easy. We come down here, we say 3 cycles equals, what is the distance? 0.3 meter. Now one cycle, which is our wavelength, will be equal to, do we know the value? No, we say x meters. So we just create the relationship. 3 cycles 0.3 meter, one cycle being wavelength equals x meter. So we see, after creating the relationship, we simply cross multiply. Alright, and then we get our answer. So we have x times 3, that will give us 3x equals 1 times 0.3, we have 0.3. So to get x, which is the distance for one cycle, we divide both sides by 3, and then that will give us x equals 0.3 divided by 3. Alright, this is 3x over 3. Obviously this will cancel this. We are dividing both sides by 3, and then we are left with x equals 0.3 divided by 3, which is 0.1 meter. Alright, so the wavelength is simply 0.1 meter. Remember, one cycle is the wavelength. So our wavelength was given to us now, which is 0.1 meter. So now we can come back to our formula, which says frequency equals wave speed over wavelength. And then we substitute. We have F equals wave speed, which is 3 times 10 to power 8 divided by wavelength, which is 0.1, and that's going to give us 3 times 10 to the power 9 hertz, which is option D. Now moving on, we have another question here again. This one says the wave motion shown above has a frequency of. So I'd like you to pause this video and quickly attempt this question. Now in this question, a diagram was given to us. They said the wave motion shown above has a frequency of. Now you discover that this axis was labeled here, unlike the previous one. Here it was labeled, you can see it is time. So this is like 0.1 second, 0.2, 0.3, and 0.4 seconds. Alright, so this is the time at different points on the wave. Now they said we should calculate the frequency. Now, a definition was also given to us for frequency. Discover that aside this diagram, no other information was given. So we'll work with our definition for frequency. What was our definition for frequency? We said frequency is the number of cycles made in 1 second. And mathematically, frequency is equal to number of cycles divided by time. Frequency is number of cycles divided by time. Now, how many cycles do we have on this wave, and what is the total time? Now, you discover that we have 1 cycle at this point, and then we have 2 cycles. So our frequency is simply going to be frequency equals number of cycles, which is on this wave we have 2 cycles, divided by what is the time, the total time taken to complete this wave. We have 0.4 seconds, so we have 2 divided by 0.4, and that's going to give us 5. So we have 5 hertz. That's the value of our frequency, which is option C. Okay, now we are going to talk about the plane progressive waves. Now, what are plane progressive waves? These are waves that transfer energy in traveling or moving away from the source of the disturbance. Basically, plane progressive waves are waves that spread out. They spread out from the point where they are produced. Okay, typical examples of plane progressive waves, or the two major types of plane progressive waves, are the longitudinal waves and the transverse waves. Longitudinal and the transverse waves. These two guys are plane progressive waves. Waves that spread out from the point where they are produced. Now, the plane progressive waves are also known as traveling waves. So already stated there, transverse waves and longitudinal waves are types of progressive waves. Now, there's something we call plane progressive wave equation, which is actually very important. It's just a mathematical representation of the plane progressive wave. And mathematically, every plane progressive wave is given the general formula, or has the general equation, y equals a sine 2 pi x over lambda minus omega t. This is omega, is also a Greek alphabet. Now, y represents the vertical component of the wave. A represents the amplitude of the wave, that's the maximum displacement from equilibrium. X is the horizontal component of the wave. This lambda is the wavelength. Omega is also known as angular velocity. Most times we interchange it with angular frequency. Now t is time. All right. Now there's something I need to add to this equation, and that is based on this formula. Please have it at the back of your mind that angular velocity, you can note it down, is also equal to 2 pi f. Angular velocity is equal to 2 pi f. 2 pi is a constant and f is frequency. If we plug in this into this equation here for angular velocity, we are going to have y equals a sine 2 pi x over lambda minus, in place of omega, we write 2 pi f. We have 2 pi f, and then we have t. All right. All the symbols have their usual meanings. Y, vertical component of the wave. A, amplitude. X, horizontal component. This is wavelength. Lambda is wavelength. 2 pi is a constant. 2 pi is a constant here. F is frequency, and T is time. All right. Now, this formula is actually very important, and this is the formula I'll like you to memorize. Okay, we are going to be using it to solve virtually all questions on plane progressive wave. The reason why I'll go with this formula, or I prefer this formula over any other formula for plane progressive wave, is because in this formula we have as many parameters as possible. We can actually use this to calculate anything. We have the frequency here, we have the time, we have wavelength, we have horizontal components, we have amplitude, and the likes. So let's see a question here. It says the equation of transverse wave traveling along a string is given by y equals 0.3 sine 0.5x minus 50t, where y and x are in cm and t is in seconds. They say find the maximum displacement of the particles from equilibrium position. The maximum displacement of the particles from equilibrium position is simply the amplitude. Remember our definition for amplitude. So basically they're asking us here to calculate the amplitude. Now, how do we go about this? Whenever you're confronted with a question on plane progressive wave, all you need to do is bring out the equation of the plane progressive wave you have in the question. And what's the equation we have in the question? We have y equals 0.3 sine 0.5x minus 50t. After bringing out the equation you have in the question, the next thing you're going to do is bring out the general equation for every plane progressive wave, the equation I asked you to memorize. And what's that equation? We have y equals a sine 2 pi x over lambda minus 2 pi ft. All right. First, plane progressive wave equation from the question, and then secondly, general equation for all plane progressive waves, the general formula, which is this and this. Now, when you're done with this, the next thing is to compare the two of them, compare and contrast. All right, you notice that at the back of sine we have 0.3, at the back of sine we have amplitude, we have 2 pi x over lambda. You discover that lambda is always with 2 pi x, is always with x. Here we have 2 pi ft. You discover that frequency is always with small letter t. Here we have 50t. So looking at what we have, what are we looking for? They said we should calculate the amplitude. So if we compare here, amplitude here on the general equation is at the back of sine. So it simply means whatever we have at the back of sine here is going to be our amplitude for this equation. Let's come back to the question. They said the equation of transverse wave traveling along a straight line is given by this, where y and x are in cm and t is in seconds. Find the maximum displacement of the particles from the equilibrium position. That is, from this equation, we should calculate the maximum displacement, which is the amplitude. So what is the amplitude we have here? The amplitude is simply what we have at the back of sine, because anything we have at the back of sine, according to the general formula, is always amplitude. So we simply say amplitude here is equal to 0.3. Now, how do we know the units to use, whether 0.3 meter or cm? Now, they already stated it here in the question, where y and x are in cm. So if y and x are in cm, it simply means amplitude will also be in cm. So we have 0.3 cm. This will be our answer, option D. Now I'm going to tell you how we are going to solve a case whereby we are asked to look for frequency, maybe wavelength or the likes. Now in this question, they said, given the progressive wave equation y equals 5 sine 200 pi t minus 0.4x, calculate the wavelength. Calculate the wavelength. So how do we go about this? The same principle. We compare and contrast the equation we are given in the question with the general equation for all plane progressive wave. Now, what's the general equation for all plane progressive wave? We have y equals a sine 2 pi ft minus 2 pi x over lambda. All right. Now it does not matter which one comes first, 2 pi ft, then 2 pi x lambda, or 2 pi x lambda, 2 pi ft. All right. This is just a way of representing it. If the wave travels towards the positive x direction, we represent it like this. If it moves towards the negative x direction, we use the other format. So this really does not matter. You just need to compare when solving. So we have y equals a sine 2 pi ft minus 2 pi x over lambda. The general equation, or the equation we are given in the question, is y equals 5 sine 200 pi t minus 0.4x. All right. So we bring out the general equation for all plane progressive waves, and then we bring out the equation we were given in the question. Then we compare. What are we looking for? In this case, we are not looking for amplitude. At the beginning, we are looking for amplitude. You can see here that the amplitude is simply 5. All right. Amplitude is always at the back of sine. So whatever you have at the back of sine is amplitude. Here, what they ask us to look for is wavelength. And where is wavelength found? Wavelength is usually found in company with x. All right. And where do we have x here? See where we have 0.4x. So all we need to do here is equate the two of them. We are looking for wavelength. We just go to find out the location where wavelength is most likely to be found, and we use x as our landmark. All right. So it simply means the wavelength is going to be here. It does not mean wavelength will not be 0.4. No. To solve this, you have to equate where you have wavelength, all right, with where you're supposed to have wavelength here. So doing that, we're going to have 2 pi x over wavelength equals 0.4x. All right, 0.4x, that's what we have here. So this is the same as saying 0.4x over 1. Now you notice for the numerator, we have x here, we have x here. Since we have exactly the same thing on both sides of the equation, and we have the numerator, they can simply cancel out. So we have this cancelling out this. Now, if we cross multiply, we're going to have 2 pi times 1, 0.4 times wavelength. So 0.4 times wavelength, that will give us 0.4 wavelength equals 2 pi multiplied by 1, that will give us 2 pi. Now, if we divide both sides by 0.4, that will give us 0.4 wavelength over 0.4 equals 2 pi over 0.4. This will cancel out this, and then we arrive at wavelength equals 2 pi divided by 0.4, which is uh, which is 15.7 meters. So this is our correct answer here, option B. Now we're going to talk about the stationary waves. Now the stationary waves are waves formed when two equal progressive waves of equal amplitude and frequency and traveling in opposite directions are superposed or made to overlap or combine together. So when we combine two stationary waves, two progressive waves rather, traveling in opposite direction, the result is going to be a stationary wave. You can see here we have a progressive wave, the one on red, moving towards the positive x direction, and then we have a plane progressive wave again here on green, moving towards the negative x direction. If we should combine this with this, we're going to have a stationary wave. Now in the combination, we have the crest of this combining with the trough of this. So this is what we have here. And then we have the trough of this combining with the crest of this. So this is what we have there. The crest of this combining with the trough here, giving us this. Trough of this combining with the crest here, giving us this. So this is our stationary wave. Now, a stationary wave has some very, very important characteristics. And what are those characteristics? There are points on the stationary waves where we call node and also antinode. All right. Now the node is the point of minimum or zero disturbance on the medium, and antinode is the point of maximum or highest disturbance on the medium. So this is our node. This point here is a node on the stationary wave, and then this point here is antinode. Here we have node, here we have antinode, here we have node also, here we have antinode. We also have node here, we also have antinode, and then we have node here as well. The point of minimum or zero disturbance, all these are points of zero disturbance of the medium, and then the points of maximum or highest disturbance called antinode. So we have nodes and antinodes on the stationary wave. Now the distance between three successive nodes is equal to one wavelength. I need you to take note of this, as we are going to use this to solve problems. The distance between three successive nodes is equal to one wavelength. So have it at the back of your mind that node to node to node is equal to one wavelength. Three successive nodes is equal to one wavelength. Also, three successive antinodes is equal to one wavelength. So from node to node to node, wavelength. Successive, meaning after this one, you take the next one immediately. And after this, you take the next one. The same thing here. Antinode to antinode to antinode, one wavelength. Node to node to node, one wavelength. Now, the distance between two successive nodes is equal to wavelength over 2. That's half wavelength. Node to node is equal to wavelength over 2. And then antinode to antinode is equal to wavelength over 2. Now the distance between a node and antinode, all right, a node and antinode is equal to lambda over 4. From node to antinode, we have lambda over 4. All right. So these equations are actually very important, as we are going to use them as we progress. Three successive nodes, one wavelength, antinodes, three successive antinodes, one wavelength, two successive nodes or antinode, wavelength over 2, node to antinode, wavelength over 4. So note it down and let's progress. Now here, this question says a wave of frequency 10 Hz forms a stationary wave pattern in a medium where the velocity is 20 cm per second. The distance between adjacent node is so what they're asking us to calculate here is the distance between a node and a node. Distance between a node and a node. Now remember, distance between a node and a node is equal to lambda over 2. Alright, so to calculate the distance between adjacent nodes, that's node to node, we need to know our wavelength. So how do we calculate our wavelength? Let's come back to our question. Frequency was given. Frequency is equal to 10 Hz. Velocity was also given. We have it in 20 cm per second. Now in this case, we don't have to convert, or there is no need to convert, because in the options here, you can see everything is in cm. So we just need to maintain this unit. All right. So we have frequency and wave speed. Now we can use this information to calculate our wavelength. We get our wavelength first, then we'll come back here and plug it into this formula. So what's the formula that connects frequency, wave speed, and wavelength? We have wave speed is equal to frequency times wavelength. And wavelength, if we make it the subject of the formula, is going to become wavelength equals wave speed over frequency. Now, what's the wave speed? We have 20 divided by the frequency, which is 10. And that's going to give us 2 cm. All right, so first of all, the wavelength is 2 cm. Now, what we are looking for is no wavelength. What we are asked to calculate is the distance between adjacent nodes. All right, adjacent nodes. So what's the distance between adjacent nodes? Is wavelength over 2. So come back here. Adjacent nodes, remember, is equal to wavelength over 2. Now what's our wavelength here? We have 2 cm. So we're going to have 2 divided by 2, and that will give us 1 cm. So this is our correct answer, option A. Now we'll be talking about the properties of waves. Properties of waves. Now there are 5 basic properties of waves. We have reflection, we have refraction, we have interference, and then we also have diffraction. Now reflection is a property of wave to bounce off a surface after striking the surface. A wave strikes a surface, it will bounce off the surface. This is reflection. Now the wave that strikes the surface, we call it the incident ray. The one that bounces off the surface, we call it the reflected ray. All right. So this is incident ray, reflected ray. Now we also have what we call the incident angle. The incident angle is simply the angle between the incident ray and the normal to the plane. This red line here is the normal to the plane. So we have our incident angle, and then we also have what we call angle of reflection, which is the angle between the reflected ray and the normal to the plane. So this is angle of reflection. All right. Now, we also have refraction. Refraction is simply the change in direction, speed, and wavelength of a wave as it moves from one medium to another. So you can see what we have here. We have a wave moving from medium 1 to medium 2. You see, as it crosses the boundary between medium 1 and 2, there's a change in direction. The wave did not maintain the original path. There was a change in direction, a slight change in direction as it moves into medium 2. So that change in direction, speed, and wavelength of a wave as it moves from one medium to another is what we call refraction. Now please take note, during refraction, speed changes, wavelength changes, direction changes. But one thing that remains constant and does not change is frequency. During refraction, please, frequency does not change. So frequency remains constant. This is a very common exam question. Now we also have what we call interference. Interference. Now interference is the effect produced when two waves with the same amplitude, frequency, and wavelength traveling in the same direction in a medium are superposed as they simultaneously pass through a given point. All right, the effect produced when two waves traveling with the same amplitude, frequency, and wavelength in the same direction in a medium are superposed as they simultaneously pass through a given point. Now, interference is of two types. We have the constructive interference and the destructive interference. This is constructive, whereas this is destructive. Now, constructive interference will give rise to a greater disturbance. Now, why? In constructive interference, we have a crest combining with another crest, all right, giving us a larger one. And we have a trough combining with another trough, giving us a larger one, all right. So constructive interference gives rise to greater disturbance or more disturbance. In constructive, crest combines with crest and trough combines with trough. So this is constructive interference. Now we also have the destructive interference. In destructive interference, the waves combine, all right, but then we have zero or minimum disturbance. Now in destructive, we have crest combining with trough, trough combining with crest. Whereas in constructive, we have crest combining with crest, trough with trough. Here we have crest with trough, trough with crest, and this will give rise to zero or minimum disturbance. You can see what we have here. So this is destructive interference and this is constructive interference. Now we also have the diffraction. Diffraction is simply the spreading out of waves as they pass through an aperture. This is the aperture here. You see that as the waves get here, they will try to kind of compress themselves and then they will spread out. Now at this aperture here, majority of the waves may not be able to pass through or will not be able to pass through. Just few of them will pass through, and the ones that will pass through will always spread out or bend around the obstacle in their path. Now, for polarization, this is the property of waves in which the waves are made to vibrate in only one plane. Here you can see what we have here, unpolarized light. You can see it is moving in all directions, all right? But then as it moves through the Polaroid, it takes the shape of the Polaroid immediately. This is the shape of the Polaroid. It assumes the shape of the Polaroid immediately. So it is now polarized or made to vibrate in a single plane, all right? This is the vertical plane here. Here you can see it was moving in all directions, in all planes. But as it moves through the Polaroid, it's now in a single plane. So this is unpolarized light. It moves through the Polaroid, it becomes polarized. Now please have it at the back of your mind or take note of it. All transverse waves can be plane polarized. Only transverse waves can be plane polarized. Only transverse waves can be plane polarized. All right, note it down. Only transverse waves can be plane polarized. Longitudinal waves cannot be plane polarized. So in other words, light waves can be plane polarized and all the other transverse waves can be plane polarized. Longitudinal waves cannot be plane polarized because they are in one plane already. All right, example, we have the sound. Sound cannot be plane polarized. Sound cannot be plane polarized, and sound cannot be plane polarized, but light can be plane polarized. All right, so that is it for this video, and I hope you enjoyed it and it was of great benefit to you. So please do well to subscribe to this channel by clicking the subscription button or the subscription icon, all right, so that you can be notified when next we upload another video. Thank you.